Hey everyone, we're going to move on to 3.4, which is the last section in Chapter 3 on probability. This one is on permutations and combinations. They are two techniques that we can use to solve more complicated probability questions, and they involve counting number of ways of outcomes. So let's look at the permutations first. It's an ordered arrangement of objects, and the key word there is ordered. So it's the number of arrangements, say, of a certain number of objects. So there's a formula for it. It's n factorial, which we'll tie into that in a minute. But let's look at a question, number one. Suppose you decide to make an easy password, and you can only use the letters A, B, C. So how many different passwords could you make? So notice here that the order matters, right? Like if your password was A, B, C, but then I typed in CBA, I'm not getting in your phone. Right? I had to get it in the right order. So how many passwords are possible? Well, I got ABC, that's one. Or I could do ACB, or I could do BAC, or I could do BCA, or I could do CAB, or CBA. And those are all different, so I have 6 of them. And that's the total number of passwords, right? So that one's pretty easy just to list them. What if we added another letter? So if we added the letter D, now I'd have to do 4 A, B, C, D, or A, B, D, C, or A, D, B, C, and this one's going to be a little longer. I kind of given up already. I guess I could do it if I stuck to it, but is there a way I can do this with a shortcut? I just need the number of ways. I don't need to list them all. So if I think about it as 4 objects, and I'm going to fill in each one. My first one, I have 4 choices. I could use A, B, C, or D. Right, so that's the number of choices there. And then remember on this, I can't repeat, right? So once I use A, I cannot use it again. So for my second letter, I'd have only 3 choices. If I chose A for the first one, then I could either choose B, C, or D for the second one. Right? And then the same argument, 2 and 1, right, would be the number of choices I have as I create my password. Now, by the fundamental counting principle, if I multiply all those possibilities together, I get the total number of passwords. So there's my kind of choice technique that I can use to find out how many passwords there are, or how many arrangements. Okay, let's use that technique for even a longer one. Now, if we have 9 letters, right? So we have 9 choices for the first, 8 for the second, 7, 6, then we just keep on going until we fill up the entire password. Now that's gonna, okay, I have to calculate that in my calculator. Well, it's not too hard to calculate that. However, one thing to note, this has a mathematical name to it. If you start with a number and just keep decreasing all the way down to 1, this is called 9 factorial. 9 factorial is 9 times 8 times 7 all the way down to 1. And there's a lot of calculators out there that have the factorial feature. If you have a scientific calculator, it's probably in there. You just have to find it. In mine, I'll bring up a TI-84 app. Let's clear it all out. I should probably go pro and remove the ads, but let's risk it. Hopefully an ad doesn't pop up. Anyway, in my little TI-84 app here, I'm going to go 9, and then I got to find that factorial button. So it's under math. See that button that says math right there? So I clicked on math, and then PRB is where all the probability features are. So I just click on PRB, and I see it's number 4 right there. I access it, and then hit enter. And then 362,880, and I go write that on my handout. I'm good to go. Okay, so use that factorial feature if you can figure it out how it works on your calculator. Otherwise, you're just going to have to go 9 times 8 times 7 all the way down. Okay, let's change it up a little bit here. Now you're going to use 9 letters, but you only want a 4-letter password. You still have a choice of 9 letters, but you're only going to do 4. Right? So my password is 4 letters long, but the number of choices I have would be like this, right? I have 9 choices for the first, and then no repetition, so I only have 8 for the second, 7, and 6. Multiply all those together, and now to get the total number of passwords for that one, which I think that's 3024. And what this does is bring us to a general rule for permutations, kind of a generalization formula. So if I look at the next page on that, permutations n objects taken r at a time. So in that example, we had 9 objects taken 4 at a time. There's a little formula for it and a notation right there. Now, actually, we'll never really use that formula. You could use it if you want, but I think it's easier just to do that choices method or just use the calculator feature. So, but let's look at the notation and the calculator feature for this problem. Find the number of ways of forming a 5-digit code in which no digit is repeated. So talking about digits, we have 0 through 9. That's 10 digits. So the number of objects to choose from is 10. So the notation for this would be 10p, and we're doing a 5-digit code, 10p5. Choosing from 10 objects, 5 at a time. My choice way of doing it, I would just start with 10 and then just keep decreasing it until I have 5 numbers. 10, 9, 8, 7, 6 is a total of 5. Okay, and then calculate that out. That turns out to be 30,240. And I'm done. Okay, so that's pretty easy as far as the calculation goes. Now, the 10p5, again, most scientific and graphing calculators will have that feature. And a TI-84, unfortunately, I can't show every possible calculator in the world, but I will do the TI-84. It's under math, so I go into math, PRB, same place where the factorial is. Check out number 2, it's NPR. And I got to put the 10 in front, and then click inside that box and put in the 5, and then enter. And I get that value again, 30,240. Okay, so that's probably the quickest way to doing it. Okay, so now we got a way to just get any permutation we want. So 43 race cars, how many ways can they finish first, second, and third? So I'm choosing from 43, 3 of them, right? And then now I have my 2 ways. I can just type that into my calculator, 43p3, or I know that's just 43 times 42 times 41. Start with the 43, decrease by 1 each time until you have 3 numbers. So either way, go to your calculator, calculate it out. You'll see that's 74,046. Okay. The next one is a little bit different. What about distinguishable permutations? Okay, this is what we're going to use if some of your objects are identical, like say letters, right? But you have 4 objects, but maybe 2 of them are A, something like that. Then we really do have to stick to this formula. So let's see how this formula works with these problems. So find the total number of distinguishable permutations or words, in this case, real or imaginary, so it doesn't have to be a real word, but which can be formed by the letters given below, right? So if all the letters were different, it would just be 4 factorial. But because that A repeats, some of those permutations in 4 factorial are going to be identical, right? Because if you swap the A's, you can't tell. So we're going to use this formula. The n is 4, so the top is going to be 4 factorial. And then how you build this is for each letter, write down how many times you see it. Like for the D, for example, there's just 1, so that's going to be 1 factorial. A, there's 2 of them, so that's 2 factorial. And M, there's 1, so 1 factorial. And that's it. Now we just got to calculate all the factorials. 4 factorial, 4 times 3 times 2 times 1, that's 24. 1 factorial is 1. 2 factorial is 2. 2 times 1. 1 factorial is just 1. Right? So pretty much the 1 factorials you can almost just ignore, because notice that bottom is just 2. Right? So this is just 24 divided by 2, which would be 12. Okay. So, I mean, that's what that denominator is for. The top, 24, is just the total number of permutations of 4 letters. But some of them are identical. We have to divide that out. All right, how about the next one, N-A-B-N-A-A? That looks like it spells banana if we rearrange them. Yeah, we can get banana out of that one. Okay, but anyway, we have 6 letters, 6 factorial. On top, at the N, there's 2 of them. A, there's 3, and then there's 1B. Right? So for each letter, just how many times it repeats, write them all down, calculate the factorials. 6 factorial calculates out to be 720. 2 factorial is 2. 3 factorial, 3 times 2 times 1, 6. 1 factorial, 1. So this is 720 divided by 12, which is 60. And that's how distinguishable permutations work. Pretty cool. I like that formula. All right. Let's just keep going. Let's just do the whole section in one video. Hope it doesn't go too long. Combination is the other one. Combination now is a selection of objects regardless of order. So order does not matter. Okay, and then there's a formula for that one too. Again, same thing. You can use the formula, but honestly, just use your calculator feature, the NCR, and you'll be better off. So an example of this, I mean, what if you're going to make a smoothie from mango, pineapple, and banana? Then if you change the order of the fruits, it's going to be the same smoothie, right? Like if you order a mango, pineapple, banana smoothie, and I order a mango, banana, pineapple smoothie, we got the same smoothie. So this is a scenario where order of the objects does not matter. All right, so let's try this one out. Suppose you're making a smoothie consisting of just 2 of those fruits. How many different smoothies are possible? Well, we could go mango, pineapple. We could do mango, banana. Or we could do pineapple, banana. If I tried to do like pineapple, mango, I already got it, right? Mango, pineapple, and pineapple, mango, same thing. Order does not matter. And so those are my 3 smoothies. The way I would write this with the notation is we had 3 fruits to choose from, and we were choosing 2 of them. So that's 3 choose 2. And that calculates out to be 3, because I just counted it up. If I didn't just list them all, I could use my calculator, right? So just go back to my calculator. If you go to Math, PRB, there's the NCR. Right? And 3, choose 2. Enter. That would be 3. Okay, so know your calculator. It's got to be in there somewhere. Maybe Google your model. It would come up. Okay, so now we got combinations. Now we can just do a bunch of them, right? 2 card combinations from those 4 cards. That would be 4 choose 2. Right, again, thinking like ace king is the same as king ace. So we're just counting how many ways we compare 2 cards together. So 4 choose 2, calculator, or list them all out, but that's going to be 6. 4 cards, choose 3, 4 choose 3. 4 choose 3 is just 4. So those really just are not a lot of work to show. Just use your calculator and it should be good. How about 5 card combos from 52? That's going to be 52, choose 5. And that one's going to be pretty big. 52, choose 5. My calculator, whoa, 2,598,960 combos. That's a lot. So if you play poker, that's how many total possible poker hands are, because poker is based off of 5 cards. Okay. How many ways can a committee of 4 people be chosen from a group of 15? 15, choose 4. Right. 15, choose 4, 1,365 ways. Right. So notice all of these examples, order does not matter, right? In this final example, if you're collecting a group of 4 people for a committee, the order that they're in doesn't matter. You're not assigning them a position or any kind of order. You're just collecting them together as a group. Okay, now let's connect permutations and combinations to probability. So here we're going to find the probability Suppose you have a student advisory board consisting of 17 members. 3 members serve as the board's chair, vice chair, and secretary. Okay, as soon as you see them starting to assign positions, that's permutations. Because now the order does matter. If you're vice chair and I'm chair, it's a different permutation if we reverse roles. Okay, so positions are permutations. All right, 3 members are randomly selected and assigned to be the new 3. What's the probability of selecting the exact same permutation you just had? Right? So that's just that one permutation. So the probabilities are always fractions. The top number in this case is 1, right? Because you want to get that exact one permutation. Now, how many total permutations are there? If you have 17 people to choose from, choosing 3 of them and assigning them an order, that's 17 P3. So key here is using P because order matters. And then calculate that out with your calculator. It's 4,080. And we're done. Okay. So a lot of these, the key is deciding permutation or combination. So you really have to ask yourself, does order matter? And there's some, clues in that as we go through some more examples. But for sure, if they're talking about committees and positions, it's always permutations. Okay, how about this one? I already put a P there to remind myself. All right, this one, president, vice president, and secretary. Yep, permutation, right? Because they're talking about cabinet members or order positions, that kind of thing. Okay, we have 12 candidates, 7 are women. We're choosing 3. Find the number of ways 3 people can be selected out of the 12. Okay, so that's pretty easy, right? Just 12 P3. Choosing 3 out of 12, and the order matters, so it's a P. Calculate that out with your calculator, or it's just 12 times 11 times 10, right, for the P. There's a shortcut for those. It's 1,320. B, find the number of ways 3 women can be selected for the 3 positions out of the 7 women. So now we only have 7 to choose from because there were 7 women, and we're still choosing 3. So this is the total number of ways that they're all women. 7 times 6 times 5, 210. Okay, and then now we can use these to do a probability question. Notice those are just number of ways, whereas C is find the probability. Anytime you're going to find the probability, it's either going to be a fraction or a decimal. That's less than 1. Okay, find the probability that the women fill all 3 positions. Now we have the numbers we need, right? The total number of ways to fill the positions is 1,320. The total number of ways that they're all women, 210. So I just got to do 210 divided by 1320, and that's, it says decimal, so 159 on that. All right. So cool. That's not too bad. Just got to get used to this new notation kind of thing. Okay, here's another example. You're dealt 5 random cards from 52. Okay. This is like a poker example. Poker, collections of cards, that's always C. Because the order of the cards doesn't matter. If you're holding them in your hand, you have the same hand regardless of how you put them in order. So we're going to do combination for this one. All right, so what's the probability that you're dealt a heart flush? All 5 cards are heart. I always like to do the bottom number first because that's just the total number of ways to be dealt 5 cards. We got 52 cards. Order does not matter, and we're choosing 5. All right, so that's the total number of ways to get 5 cards dealt to you. Now, of all those combinations, how many are just all hearts? So we can count that up too, because there are 13 hearts to choose from, and we're choosing 5. So 13 choose 5 would be the top number. And then this is 1,287 divided by 2,000, no, the 2 million, right? 2,598,960. Okay. And then if I calculate that with my calculator, I get 0.000495. And rounding that to 4 decimals, it says 0.0005. pretty low probability there, it looks like. Okay, how about the probability that you're dealt a flush? All 5 cards are just the same suit. So this one, A, was specifically hearts, but now we know there's 4 suits, so we could do the same thing for diamonds, clubs, and spades, and each one would be the same probability. So we just have 4 of those, and it's just multiply that by 4 because there's 4 suits, and we got that answer, and that's 0.002. Okay. What about a lottery? Okay, lottery is always combination, just to let you know. Because when a lottery happens, the order of the numbers doesn't matter. You just pick 6 numbers, right? You don't have to pick them in the order in which they're drawn. So for lottery, just use combinations, and you're going to select 6 different numbers out of 56. To win the grand prize, your 6 numbers must correctly match the winning 6. Again, in any order, so combination. Right? So if you think about the total number of possible tickets that you could buy, there's 56 numbers to choose from, and you're choosing 6. Right? That's the total number of possible outcomes. Right? But you just get 1 ticket. You get 1 combination of your favorite 6 numbers. So you only have 1 ticket. You have 1 chance to win out of all those. Right? And then if I calculate that 56, choose 6, that's 32,468,436. So that's the answer in fraction form. Ooh, this one says write your answer in scientific notation. So recall scientific notation. Sometimes your calculator will give you the answer in scientific notation. Let's just do this in my calculator and see what it gives me. So I'm going to do 1 divided by 32,468,436. Yeah, it does give it to me in scientific notation. You see that E -08? That just stands for times 10 to the -8th power. So scientific notation would be 3.08 times 10 to the -8th power. So 3.08 times 10 to the -8 scientific notation. Right? And remember that as a decimal. Remember how that works? You just got to move that decimal over 8 places to the left. So that would be like 7 zeros in front of the 3. Okay. So that would be the decimal. So there you got the fraction, scientific notation, and decimal for that one. Okay, let's do the last 2. Mega Millions, another lottery. Okay. So we get the first part is 5 numbers of 1 to 70. All right, so I know that's 70, choose 5. That's how the number of ways I can choose 5 numbers from 70. Oh, but then I got to choose 1 number from 1 to 25. That's 25, choose 1. So the total number of possible winning tickets for this one would be those 2 multiplied together by that fundamental counting principle. There's lots of ways on that one. And then how many tickets do you get? You get 1 ticket. You buy 1 ticket. So 1 winner out of all those. If I do the calculations here, let's see, 70 choose 5 is 121 03014. And then 25 choose 1 is 25. Okay. So if I multiply those 2 together, I'm getting 302,575,350. And that is what the Mega Millions lottery website says is the probability of winning the jackpot. It might have changed. I know they changed their ticket to like $5 recently or something like that, but that's how it used to be. Anyway, a very slim chance, 1 in 300 million, to win that jackpot. That's why nobody ever really wins. Someone's got to win, I guess. Anyway, okay. One more problem. Combinations can also be useful when solving for probabilities that involve the word and without replacement. So 18 is a problem we've done before, with a different technique, 2 cards are selected from a deck, but the first card is not replaced. Or you can almost just think of that as just selecting 2 cards at the same time then, right? Find the probability that you get 2 aces. Okay, so the bottom number is just how many ways can you select 2 cards from a deck. 52 cards, you're choosing 2. 52, choose 2. The top number is how many ways are they both aces. So there's 4 aces, and you're choosing 2 cards. That's 4, choose 2. And there you have it. 4, choose 2 is equal to 6. 52, choose 2 is 1326. And then 6 divides evenly into 1326 221 times. This is 1 out of 221. And we did it. Okay, so there's the end of chapter 3. I hope it was helpful, and email me if you have any questions. Otherwise, enjoy probability, and I'll see you in chapter 4. Talk to you later. Bye.